Hi, everybody. My name is Joe Hess-Bader. I am currently a postdoc at Duke, and I'll be presenting Module 3 of our tutorial today. And so today I'll be covering system integration and optimization. Okay, so what exactly does that mean, system integration and optimization? So there's three main parts. Part 1, I'll be looking at DBMS security and privacy, right? So how does security and privacy fit into databases? What are the different techniques that we're going to be using? Why do we even care about these techniques? Second, we'll be looking at state-of-the-art solutions. So there's a lot of great research out there currently, and we'll take a look at what are the great parts that they're using, how are they implementing these security and privacy techniques into them. And then finally, we're going to look at open challenges. So existing work covers a lot, but there's really exciting work that can come out, and it's fertile ground for future research. So part 1, DBMS security and privacy. So security and privacy, we're going to think about in two different main settings today. First, we're going to look at a client and server setting. And then second, we're looking at an untrusted cloud. Okay, so in a client server setting, we have a data owner who holds all the data. This is all that holds the private data, and they're trusted. And then we have an untrusted client who is who's querying this data owner and wants to receive some result. So in this setting, the client is not trusted to see what the private data is, however the data owner is. And so the data owner must decide, how are we going to answer the query such that we are able to accurately answer the query while preventing the client from accessing unauthorized information. Okay. Second, in the untrusted cloud setting, again, we have two parties, but in this case, we have an untrusted cloud, which is actually going to be holding on to the information and in charge of processing queries, and then a data owner or client who's actually trusted, right? And so in this setting, the data owner wants to run the query and process it on the cloud. So this is some outside cloud provider without revealing to the cloud what this information is. Okay. So these are two main settings that we're going to look at today. And the idea here is that we want to have a column ahead of time access control policy, and we want our systems to behave sort of exactly like a standard DBMS from the client's perspective, right? So we want them to be able to just send queries and receive results without managing too much else. Okay, so the idea is, first question you have would be, why can't I just add a password to my database and are using encrypted storage, right? So again, yeah, so we could say in this setting, why can't I just sort of encrypt my data and store it on the cloud, and then sort of run this query over the encrypted data. And so the problem here is that when we think about security and privacy, our attack surface is the entire stack. So the entire stack of the database system. And so our data may reside on untrusted cloud servers, and so we sort of need to re-architect our systems with security and privacy at the forefront. Okay, so we can look at if we have a naive DBMS plan on an untrusted cloud, what could go wrong here, right? So in the figure we see the client data owner, and we have this as well as a virtual private cloud or a cloud provider who's untrusted. Okay, and we could say that the cloud provider has an encrypted database where the data owner has previously uploaded records that are encrypted into this database. Okay, and then we say that, the client can then sort of query this encrypted database and receive some results over some SSL layer, and voila, they're able to send the query and receive results without letting the cloud provider know what the information is. However, this is not quite so simple, right? So there's a few things that could go wrong. First, storage. So if the cloud provider, sort of encrypts the data themselves, then that means that they're able to unencrypt it as well, right? And so you could have governments sending a national security letter or something that can compel a service provider to decrypt this data and provide it to them, thus, sort of allowing somebody else to access this private information. Second, in terms of query processing, an insider threat or somebody who's has taken over or able to compromise one of the cloud provider is able to see sort of data-dependent query traces and result sizes potentially. They can see, how long is this computation taking? What are the memory accesses? And based off that, deduce what the underlying data is. And then finally, on the client side, we could have a rogue user, so not the trusted client, but somebody else who's sort of systematically querying the database system to deduce its private contents, right? You can send query after query after query to see if figure out the entire structure of the database. Okay, so let's look at what about existing work from the security and privacy community, right? Not the database community, but all of the fantastic work that has been done outside. And so that's true. There's some great work. However, a lot of these existing S&P solutions are piecemeal, or they focus on specific steps in a DBMS workflow because they weren't thinking about databases from the start. So, for example, MPC and TEs, that we covered earlier in the tutorial, the idea here is that you'll protect data during computation. So while you're processing this information, you're not going to leak any private information. However, it doesn't really protect anything once that data is released. You could compute something, and then if the result of the query is some private information, and you release that, then you're violating, or you're leaking this information, even if you weren't doing it during the computation. Second, with differential privacy, this sort of protects data when releasing results, right? So you can say, I computed some result and I want to release it to some untrusted party. You can use some differential private mechanism to do that. So, this seems like these two techniques can work well together, right? One protects during computation, one does it when releasing results. However, composing these techniques is actually non-trivial. Okay, and so that sounds great. So where do we come in as database researchers then? So today, database research, we mostly focus on making the database systems fast and scalable. It's a really great success. We have really fast systems now. We get answers as soon as we want. It's fantastic. And for us, typically, so security and privacy is usually an afterthought, right? It's like, oh, it's this thing I have to tack on top to make sure that I don't get sued, essentially. However, the argument we're making today in this tutorial is that we actually have a lot to offer in this emerging space of making privacy-preserving analytics practical and usable, right? So if we can make regular database systems fast and scalable, then we believe we can make private and secure database systems fast and scalable. Okay, and so to this end, we have come up with the idea of this trustworthy database management systems, right? And here we have a few things that we want to support. So first and most importantly, we want end-to-end security and privacy guarantees, right? We want to cover security and privacy from when a client submits a query all the way to when they receive the results. Second, we want efficiency. We want to have efficient performance. So we want to offer performance comparable to that of current DBMSs, right? It's unlikely to be just as fast as it computing in the clear. We want something that's close enough to where people are willing to use it. Okay. Next, we want our systems to be robust, right? We want to support ad hoc query workloads and diverse user needs. We want to be able to support a wide range of applications, as wide as possible. And finally, we want our system to be useful, right? We want a UI that's like a standard DBMS that has a low barrier to entry. We want people to be able to understand our S&P security and privacy guarantees and be able to have confidence in what they're using. Okay, so the goals of our database system here is we want to have rigorous, explainable guarantees of privacy of storage, as well as computation over data. We want to have privacy for the data itself, especially under repeated querying. And then finally, we want to maximize our query result accuracy. And we also want to maximize the speed of our query execution. And the thing to notice here is that, and this is very important, is that security and privacy guarantees are not Boolean, right? There's not 1 or 0. It's not either secure or not, or accurate or not. There's actually, we can have some amount of accuracy or some amount of speed. And so this leads us to be able to make some really interesting trade-offs, right? Maybe we can sacrifice some accuracy to improve speed, or sacrifice some speed to improve privacy. And so we look at some systems later on that make this exact trade-off. But first, let's evaluate some existing approaches using our requirements here. And so first, we look at secure computation, right? This is our MPC and TEs. And these techniques protect data during query evaluation with a couple of things. First, data that's encrypted in flight, as well as oblivious data-independent execution transcript. And so this is really useful for query processing in an untrusted cloud, right? You can just upload some data to the cloud, and the cloud can carry out these MPC workload or using TEs to compute a securely and return a result. However, in this case, MPC is really, really slow. It can be up to 1,000 times slower than running in the clear. And TEs, on the other hand, which are much faster, however, they require specialized hardware and depends on sort of chip vendors to have corrective implementations. Which at the moment there's a sort of cat and mouse game between coming out with a new TE and then having people come in and break that implementation. Okay, and so the thing about MPC and TEs is they do not protect data during data release, right? So it's really only talking about during computation. And as such, if you're repeatedly querying an MPC or TE only system, you could leak information about what the private data distribution is. And, we want to say that like revealing any data. So basically, we say that here that revealing any data-dependent computation, such as intermediate result sizes, will leak private information. And we can see an example of this in the figure on the bottom right here. So here we have a query tree that has some operators associated with it. And in the brackets, we're going to be showing what's the maximum size, output size of each of these operators. Okay, so we can see with the input tables, we're assuming those are all size n. We have a filter here, in the worst case scenario, the output of this could be size n. We have a join, the output of size, worst case size of this is n squared. The second join on top of that could be n cubed, and so on and so forth. So you can see this sort of exponential increase. And the reason we have to do this is because we have to, if we didn't do worst case scenario, then an attacker could look at the size of your intermediate results and deduce some information about the input data. Okay, and so this is why we require MPC and TEs, and one of the reasons why it's so slow. And so if we look at our requirements here on the top right, we can see that MPCs and TEs, secure computation allows us to have accurate results, just as accurate as sort of plain text execution, and it also gives us great compute privacy, where you can protect data that's in flight by using this sort of oblivious execution. However, speed is lacking, so it's going to be much slower. And then also, it doesn't really protect anything query results when we're releasing data. So the data privacy is also lacking. Okay, so we look at our second approach here as differential privacy. So differential privacy reveals statistics about database workloads, database records, while withholding information about individual input tuples, right? And so it does this by injecting precisely calibrated levels of noise into query answers that's proportional to individual contributions. This is composable, so we can use multiple GP mechanisms in conjunction with each other. And we have this sort of, it provides us a nice provable guarantees on information leakage. So we can bound cumulative information leakage subject to a privacy budget, referred to as epsilon. Okay. And so DP-only systems typically add noise either to the query result that's computed by a server or the input data from data owners. Okay. So if it's on a server, then some server collects all its private data. So there's trust there that the server's allowed to look at them, look at the private records. They'll compute some result, add some noise, release the noisy result. Okay. And so that's great. So when we add noise to a query result, we have a single data owner. What's trusted, we can do this quite easily. However, when we think about multiple data owners, so for example, we have a bunch of smartphones. Each of them belong to some user who has some private data that's being uploaded to some server, untrusted server. To handle this, each individual client or data owner will be adding noise to their contribution to the result. And this leads to the situation where we have error that's proportional to the number of owners, right? So this introduces a lot of error into the system, which is not so great for accuracy. And so we can see here on our requirements or our metrics, we can see that accuracy here could be, depending on the implementation, can be lower than execution in the clear. Speed can be lowered as well because some of these mechanisms become very complex and require some overhead. But however, our data privacy is fantastic because we have these strong mathematical guarantees on information leakage. And then finally, we don't really consider, or we don't have much compute privacy in this setting with differential privacy because it does not sort of continue. It requires some trusted owner, either whether it's an individual client or an untrusted cloud server. Okay, so this leads to the idea is like, well, why can't we sort of naively integrate these building blocks into an existing system, right? And so here, have to take a look at our first problem here is we're going to be presenting. We want to prevent side channel attacks, right? So side channel attacks in terms of access pattern leakage or volume leakage or timing leakage. Okay, and so first one, access pattern leakage. This is when you have memory locations that are accessed during computation, and this can leak the frequency of values in source data. We could have volume leakage where we leak. This is basically leaking the size of our computed results. And so this leaks the number of records processed at each operator. Finally, we have time linkage. This leaks the time required for computation. And so this, meaning that the time needed to process output of each operator, right? And so if we have this information, we know the frequency of values in source data or the number of records processed at each operator or the time it takes, then this reveals some information. This is our side, all side channels that can reveal some information about the distribution values in the private source data. Okay, and this is what we want to avoid, this leakage. Second problem, we need to properly compose our techniques. So we have to combine secure computation with a DP mechanism and release to some client, right? And so if we naively did that, so okay, what if we just use secure computation or MPCs or TEs to do the computation? And then once we do the computation, we use differential privacy to then add noise and release this result, right? And this gives us a result here. On the bottom, we can see is actually, this will give us, sort of poor speed, poor accuracy, but, in addition to our great compute privacy and data privacy, right? And so that's a problem for our database systems. We want it to have great performance and we want it to have accurate results. And so next, we were going to go into is like, how can we properly compose these techniques to achieve our goals? Okay, and so for this, we're going to look at some existing state-of-the-art solutions. So the first system we're going to be looking at is called Conclave, which is it's about secure multi-party computation on big data. And so this is actually going to be a system that's mostly focused on MPC, but however, it's going to be using some very interesting, very novel techniques of leveraging the database structure in order to improve MPC performance. Okay, and so what it does is basically it has a compiler for relational queries that accelerates secure computation. Right, so what this means is how it does this is instead of directly converting SQL queries into secure computation blindly, just taking the whole query and constructing an MPC program, what it does is it transforms these queries into combinations of small data parallel local clear text processing as well as small MPC steps, right? So you can see here in the figures, instead of converting all of these operators into MPC, it takes portions and pieces of it. Can we do some small portions in MPC with the rest in clear text, only when necessary? So in this way, we're able to reduce the amount of MPC or secure computation necessary in order to drastically improve our performance. And so the great thing about the system here is that it's able to prevent side channel attacks, and it also improves speed through less MPC. However, it still does require some expensive MPC, and it only really, at the moment, considers protecting data during computation. And so if we evaluate on our metrics here, we can say, great accuracy, great compute privacy, speed is okay, but can be improved. And then finally, we don't really have any data privacy in this setting. Okay. Our second system that we're looking at is called Opaque. And this is an oblivious and encrypted distributed analytics platform. And so this is a distributed analytics platform built on Spark that utilizes TE's secure enclaves for oblivious execution. And the way this is, it introduces oblivious relational operators for rule and cost-based query optimization with security and privacy guarantees, right? And so it has to sort of rewrite these operator implementations to support TEs. In doing so, it's able to sort of, provide security and privacy for our query execution. And so this is great. Prevents side channel attacks and improves speed for TEs. Downside here is it requires specialized hardware and again, only protects data during computation, right? And so for our metrics, great accuracy, speed is much improved, great compute accuracy, but again, does not really consider a data privacy or the privacy of the data that's released. Okay, so our third system we're looking at is called shrink wrap, which is secure query execution with DP guarantees. So full disclosure, I am the first author in this paper, so maybe a little bit biased. But so here we have some extended security and privacy guarantees with differential privacy. We're going to combine differential privacy with MPC. And we want to cover, sort of prior knowledge of data owners with respect to query answers, cumulative privacy loss from repeated querying, as well as collusion among data owners and the client. And so the way we do this is we reveal noisy intermediate cardinalities at runtime for speed up. So instead of doing worst case cardinalities every single time at every output of every operator, we're going to be using differential privacy to create noisy versions that are smaller. Okay, and in addition, we noise query result answers in MPC at the end, such that the true answer is never revealed. Only noisy result is revealed. Okay. So we can see here in the red, you can see the worst case oblivious execution sizes, and in the blue, in the brackets, we can see a noisy intermediate cardinalities. Okay, and so great things about the system: it prevents side channel attacks and improves speed through TP volume. However, it does still require user-defined trade-offs. So the user will be in charge of figuring out, how do we set epsilon? How do we apply differential privacy? What is needed? And also, there are limits on repeated querying because it uses a privacy budget from differential privacy. You can only query so often without until your privacy budget is totally consumed. And so you can see in terms of our metrics, we can see accuracy is all right, pretty good. Speed is also pretty good, not as good as clear text. Our data privacy does well because we have differential privacy to provide our guarantees. And finally, compute privacy also does all right because of we're using secure computation here. So you can see here, in this system, it's the first system that is able to achieve good ratings at least in all of our metrics, even though it's not the best in any of them. Okay. And then the next system that we're looking at is what's called crypT. So this is crypto-assisted system that combines MPC with DP to execute database queries over data that's collected from multiple data owners. Okay, this achieves a strong accuracy guarantees without requiring data owners to upload private data to some central trusted data collector. Okay, and so here we have a way of converting local differential privacy where we have individual users adding noise to each one, where we have an error that's proportional to the number of users, into something like central differential privacy, where we have a single owner that adds noise once. Okay, so to reduce the amount of error. And so to do this, it uses MPC to serve as this sort of trusted server without actually requiring a trusted server. Okay, and so great thing here is that it can ensure privacy through differential privacy and improves accuracy through using MPC. Downside here, it does require some expensive MPC computation and only supports linear aggregate queries. So again, similar to shrink wrap, the system is able to achieve some amount of accuracy, speed, data privacy, and compute privacy, depending on the settings that the user selects. Okay. And so those are kind of the main state-of-the-art systems that we have. There's many more. Again, this is a very non-exhaustive list. And I can encourage you to reach out or to ask questions about other existing systems that do a fantastic job as well. Okay, so the final part of our module today is going to be our open challenges. So there's some exciting research work or ideas that can come out, and then we're really excited to see how other people tackle these challenges. So first, we're thinking about is growing databases. So all the databases we sort of discussed before sort of mostly consider the static setting, where the data is set once, and then we have some system that runs on top of that. So when we have a growing database, right, this is where records are constantly coming in, and the data is not static anymore. And so in this setting, we have an additional linkage, which is called update pattern linkage, right? So the update pattern, or how often the timing of these updates actually reveals some information about the source data, which could sort of violate our privacy guarantees or result in privacy breaches. And so this requires some further countermeasures that hides update patterns. And I believe there's actually a paper here in Sigma 2021 called DP Sync that sort of handles this update pattern leakage. And so for an example of a real world privacy leakage from growing database, you have some secure outsourced database. You have two IoT sensors. You have a person, right? So the person walks through, they go through one IoT sensor, and this sensor will then sort of back up an encrypted IoT event. A person goes to a second IoT sensor, and again, the sensor backs up some encrypted IoT event. And we can see that based on when these sensors update, the update pattern of these sensors are when these updates happen, you can determine, oh, what was the path that this person took, right? And so you can see floor by floor is like, okay, these sensors were tripped, therefore this person, based on these updates, this person took this path through these floors. Okay, and you can use sort of average walking times or something to induce this. Okay. Yeah, and so with that, you're able to learn the location that this person went to, which is a privacy breach. And so this is because the event time is strongly tied with the backup time, right? Let's call it a database update time. And an adversary can breach this privacy by using the time information of updates. And this type of attack generalizes to any event-driven update where the event time is tied to the data upload time. And so the challenge here is like, how can we decouple this event time from the upload time while sort of preventing, while still achieving, timely information? And it's just the Sigma, again, this is the paper DP Sync that's in the conference. Again, this full disclosure, I'm an author on this as well, but I encourage you to seek this out. And finally, with some additional challenges, right? We have to think about transactions. If we have asset transactions, how does this work in a security and privacy setting? Second, how about floating point support? How do we do this? In differential privacy, there are a lot of leakages that are attacks based on floating point. How can we sort of handle this in a database setting? And finally, we have query interfaces. So we have these additional security and privacy parameters. How do we present this to users? How are they able to sort of either set it or find it automatically set? And as well as how do they even understand what this means? What does privacy leakage mean to them? How, if our accuracy, how can we provide sort of confidence intervals on our accuracy, or give them any sort of intuition about this through the interface? And finally, just to conclude, there are three main topics that we talked about today. We're looking at, sort of security and privacy require advanced techniques beyond just sort of simple passwords. We have, existing solutions that blend techniques such as MPC and DP to negotiate trade-offs. And finally, there are many open challenges that exist that require additional research work. So hopefully through this module today, you learned something about sort of system implementation and optimization, and we're happy to answer questions. So either feel free to reach out, ask questions now, or to email us or seek us out. So again, thank you so much for your attention, and looking forward to seeing you in the next module.